Hi, and welcome to our section on integrating compiled code into our Python programs. We're going to take a look at the benefits and drawbacks of our compiled code and see two ways of making the connection between Python's managed environment and code that runs directly on the hardware. In this first video, we're going to see what we can gain by using compiled code for part of our program and what it can cost us. Python is a very productive language, but it's not all things to all people. Sometimes we need to interface with code written in a different language. One reason for doing this would be if we need to access some functionality that was written in a different language. As long as the code in question is in a dynamic library that has a C-compatible interface, it's relatively easy to call the code from within Python using the foreign function interface provided by Python's standard C-types package, which we'll discuss in the next video. Alternatively, maybe we need to write some code that runs close to the metal, either to maximize the performance of an algorithm that's proven to be a bottleneck in our project, or to interface directly with some piece of hardware, in which case we'll want to be compiling custom code and linking into the Python environment. That's most easily done using a tool called Cython, which we'll discuss in the third video of the section. Those three reasons, interfacing with existing code, optimizing a bottleneck, or driving hardware, cover more or less every case while working with compiled code is actually a good idea, because there's some significant downsides to working with compiled code. First and foremost, among these downsides is the fact that it's easy to create ridiculously weird bugs when we work at that level. Both C-types and Cython allow us to make a horrible mess in the program's memory, potentially producing any conceivable bug or error. When we're lucky, that results in the flat-out termination of our program due to violating the constraints of the operating system's protected memory manager. I say that's lucky because if that doesn't happen, it means we've made an effectively random change to some part of our program state. And who knows what they'll do. The second downside is that it makes distributing our program more difficult. For a normal Python program, we can distribute a single .pyz file to our users or upload a setup tools compatible source package or operating system neutral wheel file to the Python package index. Using compiled code means we have to worry about which operating system and hardware architecture our users employ, and provide separate packages for each combination we want to support. The third downside only applies if we're writing our own compiled code, primarily for the use cases where Cython is most useful. The problem is that it can be non-trivial to actually get a compiler installed and working, particularly for people who aren't used to working with compilers. Not only that, if we distribute our project as source code, our users need to go through the same hassle. Between the danger of bizarre errors and the annoyance involved in creating and distributing projects that use compiled code, we should generally wait until we have a compelling reason before we take the step of creating or interfacing with compiled code. Now we have a pretty good grasp of the benefits of interfacing with compiled code. It gives us access to C-compatible libraries written in other languages. It lets us optimize the performance of critical algorithms, and it lets us interface directly with hardware or low-level drivers. Similarly, we know what the drawbacks are: the potential, seemingly inexplicable errors, and a generally higher level of annoyance and difficulty throughout the development and distribution process. In the next video, we're going to look closely at the C-types package and use it to interact directly with the C standard library.